of your postgraduate students? Okay. Humanity. As you know, concrete has gained that importance only because of its moldability, strength, durability, and low cost. What is the meaning of moldability? You can make structural element of any shape, any size using this material. Of course, as long as it is in green state, fresh, and with minimum effort you can gain good strength, and with minimum effort you can gain good durability. When I say durability, obviously I am talking about performance during the service life of the structure. Of course, all this is happening at a very low cost. If you compare to steel structures, the cost of concrete is very small. Roughly, if you say 1 cubic meter of concrete, how much does it cost? Around 5,500 to 6,000 rupees, say a good brand, 6,000. It gives you about 2.4 tons of material. 1 ton of concrete costs around maybe 2,500 or something, 2,300 rupees or something. 1 ton material. 1 ton of steel, how much does it cost? 70,000. So there is no comparison at all, isn't it? So that's why concrete is so popular. That is one of the major reasons. It is very low cost material. Then, of course, after these ingredients of the concrete, you have the Portland cement concrete, major concrete. And as we know, cement industry is responsible for the carbon emissions. Most of the carbon emissions from the construction industry, you can see approximately 6 to 7% of the total carbon emissions are caused by the cement industry. Every country says we have to cut short these carbon emissions, we have to bring down the pollution. Everybody says, but what initiatives we are taking? When you come to look at the initiatives, they are very vague. As a civil engineering professionals, it is in your hands to bring down this 6 to 7% of carbon emissions to the lowest possible level. That is possible only when you minimize the consumption of OPC. If you can bring down the consumption of OPC, what is OPC? Ordinary Portland cement, whose manufacturing results in emission of lot of carbon dioxide and carbon monoxide, carbon emissions. So that's what we have been saying. If you see any OPC brands, 33, 43, of course, those are outdated. Now we are having only 53 grade OPC, and 1 ton of this OPC cement manufacturing releases around 0.8 to 1 ton of carbon dioxide emissions. Can you imagine? So if you are saving 1 ton of cement from using, then obviously you are directly impacting the carbon emissions. That is the need of the hour. That is the need of the hour. So the reduction in these CO2 emissions may be achieved through the development of alternative binders, alternatives for OPC, in the form of GGBS, fly ash, rice husk ash, methacrylate, silica fume, microsilica, so many mineral, don't call them admixtures, they are additives. There is a slight difference between admixture and additive. It is crossing certain limit. There is a bar, 5% if it is called exceeding, then you cannot call it as admixture, you better call it as additive. That's all. That is a excellent. Now we see the construction industry globally. Progress of any country is determined by the construction activities that take place within that country. There is an increased growth of the huge investments put in by the government and also by public and private organizations. Infrastructure projects, the investments in these projects will clearly say the progressive nature of the country, economic development. It's predicted that growth in the urban infrastructure will be around 65% by this year. China will be on the top of the list of economic growth, followed by us and USA. 4 countries, namely China, India, US, and Indonesia. These 4 countries are accounting for about 58.3% of global growth in construction. Remember, almost 60%. These 4 countries. See, if something can be done with respect to the consumption, making cuts in the consumption of cement, that will definitely have an impact on the carbon emissions and other related issues. Next one. You can see here China 32.5%, India 13.3%, US 12%, and Indonesia 6.8%. Put together, around that's coming around 58 or close to 60%. Next. If you take our country's scenario, India's GDP growth of about roughly 8%, which is contributed by construction industry in India. Obviously, this has got very good impact on the economy. We are expected to emerge as the second largest globally by 2030, contributing to a growth rate of 7.1% by each year. The growth drivers are mainly the development of smart cities. That has been the buzzword during the past 1 decade, last 10 years. Smart cities, then industrial corridors, then you have got mega ports and an increasing demand for commercial space. All these projects will involve the consumption of huge quantities of cement. So if you can do something to bring down the consumption of cement, OPC, then definitely you will have direct impact on the topic of the FDP. You have to take up a construction practice which is sustainable. Next one. Okay. Right now, more than 5 billion tons of cement and 10 billion tons of concrete are produced annually, and substantial increase in these numbers are anticipated over the next 3 decades, next 30 years. You cannot imagine 5 billion tons of cement consumption. Then cement production accounts for 6% of total greenhouse gas emissions due to the process, fuel combustion as well as limestone decomposition. Both these activities. You'll be knowing these 2 activities in your cement manufacturing procedures, building materials or building material construction technology. So as to reduce globally these CO2 emissions from cement industry obviously must be brought down. Mitigation strategies are covered at length. At this point of time, the use of low carbon supplementary cementitious materials. Low carbon supplementary cementitious materials to replace OPC is one of the most promising strategies to reduce carbon dioxide emissions. Next one. Just now we discussed. Next one. Right. So with this aspect in mind, the industries involved in the manufacturing of cement are finding ways to reduce the emission of carbon dioxide so as to meet the guidelines of Paris Agreement on climate change. I think we will have a detailed discussion on this aspect in the afternoon session by Professor Balaprasad. To meet this standard, it is expected that there should be a fall of 17% of the annual emissions from cement industry by 2030. That is our target. By 2030, we should bring down these emissions by 17%. Next. So, incorporation of now waste or byproduct generated from industries incorporating the concrete. That is the next one. This GGBS, where from you get GGBS? Ground granulated blast furnace slags. Where from you get? Which plant, which industry? Steel industry, steel manufacturing, reduction, and flash, thermal power plants. So these two are waste as far as those industries are concerned. But we should call them as byproducts as far as civil engineers are concerned. Because when you are utilizing them in making concrete, how can we call it as waste? It should be called as byproduct. That's why those two are misnomers. You can interchangeably use those two words. So various experimental investigations have been carried out to understand the feasibility of use of these products from industries. Next one. Now you see, cement plus water results in CaSO gel and calcium hydroxide. That you know. Yes or no? Basically. Next equation is interesting. CaOH twice plus pozzolanic material like fly ash or GGBS or something like that. In the presence of water, it is leading to CaSO. Suppose if you are replacing OPC by these ingredients like GGBS or fly ash or any other mineral additive by certain person, I don't know how many of you have observed the attainment of strength will be relatively slower. Do you know it? When compared to OPC, the blended cement will attain its strength slightly at a lower rate. What is the reason? This is the reason. OPC only reacts with water to release CaOH twice. That released CaOH twice will come in contact with this pozzolanic material or additive, mineral additive. In the presence of water, that forms the CaSO gel, which is responsible for cementitious material. So to release of CaOH twice and consumption of the CaOH twice with pozzolanic material to lead to develop CaSO gel, that takes some time. That is the reason why early strength gain in blended cements will be relatively slower. You cannot expect 7 days strength gained by OPC cement. Suppose if it is 53 grade cement, 7 days strength will be almost close to 50 MPa. I don't know how many of you have observed. I'm talking about cement compressive strength. But when you use it with blended cement, fly ash based or GG based, that strength attainment will be definitely not up. It will be the order of 35 to 40 MPa at the end of 7 days. Only the expected strength is attained at the end of 28 days. Earlier strength will be relatively slower in the blended cement. This is the reason. Okay, next one. Okay, next. Right. I was mentioning 1 ton of Portland cement clinker releases 0.8 to 1 ton of carbon dioxide into atmosphere. You see the equation, limestone, which is called calcium carbonate, CaCO3, when it is burnt at 1000 degrees centigrade, it is releasing calcium oxide and carbon dioxide. See the proportion, 100% of limestone is releasing about 56% of calcium oxide and 44% of carbon dioxide, almost 50% carbon emissions. So 1 ton of cement contains about 620 kg calcium oxide. Therefore, CO2 from limestone itself is 4x gas. The equation is self-explanatory. So you can understand that from fuel burning, carbon dioxide release will be around 320 to 450 kg. Put together, it will come around 0.8 to 0.9 tons carbon dioxide emissions in the production of 1 ton of OPC. So that emission somehow you have to bring down. There are two aspects. One is your natural resources are getting depleted because you are where from you are getting these clinkers, raw resource material you are digging your earth crust on, isn't it? So release depletion of resources is happening, and in digging those resources you are using again depending on power. That power production is releasing some carbon emissions. Manufacturing of cement itself is causing again burning of fuel, grinding of this clinker. Everything is consuming power, which is again causing the release of emissions. So if you can bring down the consumption of cement itself, straight away it will have very good impact on the carbon emissions and it will lead to a better environment. Next one. Same in the form of picture I am showing. See, around 50% of carbon dioxide produced comes from calcination of limestone. That is heating of CSCO2. Worldwide cement production produces around 7% of carbon dioxide emissions. Keep these points in mind. Next one. Okay. Now comes the alternative. So far I discussed the importance of obtaining or looking at alternative binders, alternative to OPC. Now how can we have? Best is alkali activated materials. If you can use 100% slag and 100% fly ash in a concrete, can you imagine? That has got that capacity. Only thing is it needs to be activated. You need to activate that reactions. So development of alkali activated materials as an alternative for Portland cement is gaining interest after more than 100 years of periodic usage due to increase in the CO2 emissions. Alkali activated materials are produced through the reaction of alkali source with an aluminum silicate containing solid precursor. Aluminum silicate materials used as source materials for alkali activation are these industrial byproducts. Nowadays, the alkali activation of GGBS is receiving significant attention as alternative cement binder. Alkali activation of GGBS. Next one. Next. Most common industrial byproducts used as binder, these two. GGBS has been widely used as cement replacement due to its latent hydraulic properties, while fly ash has been used as pozzolanic material to enhance the physical, chemical and mechanical properties of cements and concretes. We will be discussing that. Next. Right. This also discussed. Next one. Right. There are two models of this activation of alkalis, alkali activation. Model 1, if you see carefully, activation by low to mild alkali of a material containing primarily silicate and calcium will produce calcium silicate hydrate gel, CSH gel, similar to that formed in Portland cements but with a low calcium to silica ratio. What is happening here? Activating. What is getting activated? Silicate and calcium. Any material containing silicate and calcium by using low to mild alkali. Second model is activation of material containing primarily silicate and aluminum, not low values, using highly alkaline solution. These two models. This reaction will form an inorganic binder through a polymerization process. That's what. First one is known as alkali activated slag concrete, AASC. Alkali activated slag concrete, AASC. Second one is leading to your GPC, geopolymer concrete. So what is happening in the model 2? Activating material containing primarily silicate and aluminates using a highly alkaline solution. This is chemistry. Don't worry about that. Next. The term geothermic is used to characterize this type of reaction from the previous one, that is ASC, and accordingly the name geopolymer has been adopted for this type of binder. The geopolymeric reaction differentiates geopolymer from other types of alkali activated materials such as ASC, since the product is a geopolymer rather than CSH gel. You have to differentiate CSH gel and this polymer slightly. That is what we have in geopolymer concrete. Next. This also we discuss. Next. Geopolymers are sustainable and eco-friendly material. Examples: Metacline, Ricer's Cache, Silca Fume. These are also coming up. Some students have worked on Ricer's Cache also, I think, at Anna University, some scholars. Next. So by completely eliminating the usage of cement, this geopolymer emerged as green and sustainable construction material. That's what. I hope you got me. The objective is to completely eliminate the usage of OPC. We are not going to use any more OPC. We are using either GGBS or fly ash, which are considered to be industrial byproducts. Another advantage is this fly ash or GGBS, their disposal itself is a major headache for the industries that are producing. See, if you take Simhadri Thermal Power Station at Visakhapatnam, disposal of fly ash itself is a major headache for the plant that is producing power. So if that fly ash is utilized properly for making concrete, it's a very welcoming step. Your waste is getting utilized. By doing so, your disposal problem is solved to some extent. That is one aspect. Second thing, you are minimizing cement OPC consumption means you are saving your natural resources. Depletion of resources cut short. I mean, depletion is made of. Next. Now you can see constituents of geopolymer concrete. Just have a look at that one. Different ingredients. All the left hand side are alumina and silicate sources. All those materials are having aluminate and silicate, which are activated by some alkaline medium. That alkaline medium is top one, you can see, alkaline sources, caustic soda and potassium hydroxide, KOH and KOH. The right side materials are common for any concrete: gravel, coarse aggregate, fine aggregate, and water. So new thing is, anywhere do you see the presence of OPC? OPC is completely eliminated. We are using only industrial byproducts. One of those industrial byproducts. Okay. Another advantage is durability is increased because of this GPC. How durability can be ensured? What is the difference between conventional concrete and GPC concrete? Conventional concrete is having major component of binder in the form of OPC, and here minus OPC, you are having binder in the form of fly ash or GGBS or some other mineral additive. What is the reason for the increase in the performance or durability? What is the average particle size of OPC? Around 45, average is 45 to 50 microns you can take. Whereas GGBS or fly ash or silica fume, microsilica, these particles are, you can get them even as small as 6 to 10 microns. Can you imagine? So whatever small voids are in between OPC particles, those voids also can be filled by these smaller particles. So your voids in concrete are much more minimized. The problem for concrete is always through the voids only, isn't it? If you can minimize the presence of those voids, obviously the performance of such material can be better, you can expect. That's how durability of this material, especially in a place like coastal area. This is also coastal area. Or Andhra Pradesh, entire coastal belt we are having now. So in such places, this type of concrete is a better alternative for OPC concrete or conventional concrete. Next one. Better performance of geothermal concrete. Earlier investigations confirmed the outstanding performance of geothermal materials in terms of early strength development, resistance to acid attacks, good freezing thawing cycles, provides to be a suitable fire resistant material. How early strength development? That's not a big issue. Resistance to acid attacks, I told you. How can you expect the material to be better acid resistant? When the voids are minimum or smaller, obviously the entrance of this unwanted material into concrete and reach your rebar will be minimized, and hence performance of that RCC structure will be better. Third one, good freezing and thawing cycles. What do you mean by freezing and thawing? See, water, if the material is having voids, water will enter into voids. When the ambient temperature is falling down, say below 0 degrees, minus 10, minus 15, then what happens? The water particles in these voids will try to freeze. When that water is frozen, what happens? Its volume increases. That increase in volume causes cracking. Those cracks will lead to deterioration of the material and poor performance of the material. So that problem is relatively reduced here when you are using a material like GPC concrete. And also it is proved to be a better fire resistant material or heat resistant material, as some studies have shown its resistance and performance better up to even 1200 degrees centigrade. 1200 degrees centigrade exposure for a concrete structure, the practical cases are very, very less. Most of the times, if any accidental fire takes place, the temperature may be in the order of 200 to 300 degrees centigrade. Of course, that too depends upon the material stored in the structure. Combustion characteristics of that material stored in the structure. But most of the times, majority of the practical applications, the structures coming in contact with high temperatures will be in the order of 200 to 300 degrees centigrade. But studies have shown that the material is showing its performance even up to 400 degrees centigrade. Even in our laboratory, one of my scholars has worked up to 800 degrees centigrade. It's good. Relatively better. Next one. So these are the areas where you can use GPC. Okay. Next. Some applications I have shown you. Next. Right, you can see here. Precast geopolymer concrete floor panels. You can see. Why precast? See, curing is sometimes required by means of heat curing. This type of concrete requires some 60 to 80 degrees centigrade temperature curing, heat curing, or otherwise ambient curing. Ambient curing means you don't need to drown them fully in water. That is very common for conventional concrete structures, isn't it? But here in GPC, you don't need water to cure it. Either you leave them at room temperature or ambient temperature, or you can heat it. That heating will accelerate the chemical reactions, and then it will lead to attainment of strength at a relatively less time. So your curing modes will be two curing modes. One is ambient curing, another one is heat curing. When it is heat curing, obviously the structural member should be precast elements only. Yes or no? You cannot heat the concrete member inside. Yes or no? So that's why these concrete panels are precast floor panels. Next, you can see fire resistant wood chipboards. You can see. Then pilot and industrial equipment, you are applying that geopolymers. Even electrical fuses are also manufactured by some sort of geopolymers. You are producing brick with LTGS on kaolin soils. Next, you can see aircrafts, lightweight aircrafts, Rafale. In the manufacture of Rafale, I think French product Rafale. French, they use these geopolymer concrete panels in the manufacture of those warplanes. And on the right side, you can see pavement repair materials. Decorative items also manufactured by this geopolymer concrete. And you can see some resin material, foamed geopolymer resin material on the right side, bottom. These are all few applications. Next. Then you have to look at the other side of the phase. Limitations. Maintaining homogeneity in the source material such as flash is a challenge, big challenge for the use. Because when you are using flash, it's not in your control, isn't it? It is not a factory product. It is produced by thermal power plants. The flash, most of the times that is available in India, is belonging to which class? Class C and Class F as per Asian classifications. In India, most of the coal combustion results in Class F flash. So the characteristics or properties of this flash may vary with the source material of your coal, pulverized coal. When that is changing, your J-polymer activity will change, your alkyne reactions will change, your product performance will change. There's a big challenge to maintain that uniform source of this flash. That is slightly difficult. Then purity of alkaline solutions, alkaline materials, as I told you, caustic soda, NaOH or potassium hydroxide KOH, all these are alkaline source materials which are used to activate your GGBS or flash. So it is very difficult to find pure materials of this nature. Most of the time that is a complaint from our scholars or postgraduate students. Because there will be two varieties, if I remember it correctly. One is industry product, another one is research product. So they will give you industry product for research purpose. They don't know the importance of this one. So that's why your results may get altered because of the issues related to purity of alkaline materials. Then another one you see, requirement of heat curing either by steam or by dry heating for setting up GPs is another major limitation. One thing is you can leave it at room temperature, that is ambient curing. Naturally it will take more time. But if you want the product at a faster rate, you need heat curing, for which you need to provide extra infrastructure facilities. Next. High alkalinity environment poses health hazards to the people involved in the concreting works. Cost of alkaline solution is high depending on the purity of its alkaline. This is the costly material. Alkaline material, NaOH, KOH are related materials, Na2SiO3, I will show you some other materials. These are not cheaper materials, so they have got bearing on the unit cost of concrete. Unavailability of widely accepted specifications and guidelines, that is another issue. Because these chemicals as well as industrial byproducts should satisfy some minimum specifications. Production of GPC requires great care in contrast to conventional concrete. Obvious, because when you are using costly chemical to activate these byproducts, you need to be very careful about the dosage of the materials. So you need to be very careful. As we know, on lighter cells, if you can say conventional concrete, no engineer will be present at the time of making conventional concrete. But you cannot leave like that this GPC. You have to demand the presence of a trained engineer, no doubt. Because the situation is demanding. As long as the material is applied frequently and in many products and the knowledge is shared among all the concerned groups, then it will come one day like a conventional concrete. But till then, you have to be very careful in producing this GPC concrete. Next one. So these are the key components of GPC. Source materials that are GGBS, flash, metaclame, isoscale, red mud, and GGBS. Alkaline solutions, sodium hydroxide or sodium silicate. These solutions initiate the geopolymerization reaction when mixed with the main source materials. So when you look at the geopolymer reaction, the chemical reaction between the source materials and alkaline solutions source material is byproduct. Alkaline material is sodium hydroxide or sodium silicate. These reactions result in the formation of a three-dimensional network of polymeric chains known as geopolymer. That's a geopolymer reaction. These chains provide the binding matrix in geopolymer concrete. That is the crux of your concrete. So whatever the role is played by OPC in conventional concrete, that role is played by this product, which is obtained as a result of chemical reaction between source material and alkaline material. Next. Drawbacks of this conventional concrete, first one, that is the objective of our topic of this FDP, isn't it? You want to show some civil engineering practices which are sustainable. Major concern is with respect to our high carbon release during the manufacture of OPC. Another one is consumption of resources, natural resources. So if you keep on consuming the resources, one day what will happen? You will end up with no resource at all. Then energy intensive. And another thing is, at this point of time I would like to share, this OPC, even if GPC is not there, some other material is coming up, OPC definitely will be getting stopped for its production shortly. Already major brands have stopped the production of OPC 53 grade. Are you aware? You don't find major brands of OPC now in market. At least 50% of the plant they are shutting down in producing this OPC. They are focusing on some blended cements like PPC or PSC, wherein you are using only about 30 to 40% of these industrial byproducts. Instead of using 100% of OPC, I am using only 70% of OPC and remaining 30% I am replacing with some industrial products. But that is also not the end of the story. What will happen if OPC is stopped and PPC is continuously used for another next 20, 30 years? What will happen? One day you will end up with non-availability of fly ash. That is expected, I tell you. In future, you will not find fly ash because that is consumed everywhere. And another important aspect is now for power generation, solar and wind sectors are developing at a faster growth. So people are looking at those sources of making power. That is leading to the production of fly ash itself. So fly ash production is coming down, consumption of fly ash is increasing. So that will end up at one day non-availability of fly ash. So you have to look at some other alternative to PPC or PSC, slag cement. That day is not far away. Maybe another 15-20 years you will see. Already we never, as a student or as a young faculty member, I never imagined that OPC will be going out of market. Now it is happening, already started. So another 15-20 years definitely these fly ash based cements also will disappear from the market. You have to look at from some other alternative materials which is possible by young blood like yours. You have to look at those alternatives. So energy intensive, that is another product. Another drawback of conventional concrete is energy intensive. It consumes a lot of energy in preparing this cement. Then it is also producing a lot of heat. It requires curing requirements. What do you mean by curing requirements? For curing also you need water as good as potable water. Of course, how we are adhering to this specification, that is $1 million question, but as per specification, you are expected to use potable water for curing also. Then limited resistance to harsh environment. Why? Conventional concrete is having the possibility of voids in the range of 30 to 40 microns. That itself is sufficient in a place like Visakhapatnam, where the ingress of this humid salinity, when it is entering into your concrete through these pores, it will take less than 10 years to deteriorate your concrete. Then longer setting time, that's another headache. Next. Advantages of geothermal concrete. The list is there, you can read them and you can understand because already I have explained. Lower carbon footprint, utilization of products, resource conservation, high durability, rapid stress development, fire resistance, lower heat of hydration. Obvious, isn't it? The heat of hydration is lower. This heat of hydration is causing a problem of shrinkage cracks during the early ages. That is also minimized here. And sustainable construction, long service life. These are all advantages of geothermal concrete. I hope all points I have covered while discussing. Right? Next slide. Adaptability of alpha-fine based geothermal. That is the what I want to present now. Ma'am, time constraint everyone. So, in this work, I want to present work wherein we used alkafine also another mineral admixture along with the conventional GPs constituents. Next. Next slide. This also I discussed. Okay, just let me quickly go through that. Geothermal concrete is made by using alumina and silica-rich materials as precursors. Okay. What is time? Now. Okay. Right. Okay. Geothermal concrete needs. Okay. Precursor. What is precursor? These materials. These are industrial byproducts which are rich in alumina and silica. They are known as precursors or binders. This geothermal concrete needs hardener in addition to the precursor, the formation of this chain-like structure similar to geolites. This process is known as polymerization, geopolymerization. Obviously, this geopolymerization requires alkaline medium. Sodium silicate is needed to provide active silica in the alkaline medium. This active silica initiates the reaction and forms three-dimensional network of silico-aluminate structures like polysialate, SiO, polysialate siloxo, that is SiO, AlO, SiO, and polysialate disiloxo. Two SiO2s will be there at the end, if you observe. This is a chemistry. Next. Those three I am showing that stuff. Next. Okay, let us next one. Okay, in this addressing a recent gap on the performance of geothermal concrete under elevated temperatures, you have got to develop an optimum mix wherein you have got so many variables. Variables like alkafine I am adding, that doses, geopolymers to solids ratio, that's one thing. Alkaline medium doses, you have got involvement of so many materials. Only thing is 100% the slag or 100% fly ash I am using. Here I have used fly ash, but you have got so many variables, involvement of variables. So if you want to do the research work on a final product, you have to get a mix that uses minimum resources and will give you the target strength. Suppose if I am trying to achieve M30, my target strength is around 38.25 MPa. That I have to achieve by optimizing all these ingredients, especially this chemical alkaline resource materials, because they are costly material. So for that, I have used some optimization techniques here. Optimization technique by name Tabuchi method. Heard of it? Tabuchi method. You must have heard somewhere. But that is one optimization technique. Tabuchi. Next. The objective of this optimization technique uses is to reduce the time for experimentation. Why I should reduce? Because variables are many. If you want to optimize the time of project, you have to use some optimization technique. Obviously, it will lead to reduction in cost of experimentation. Number of trials will be reduced. Labor, money, resources, everything will be reduced. Next one. Next. Methodology selected. Okay, these are all optimization techniques. Next. 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 Right. I am skipping intentionally that optimization methods and all that. Now you see the resource materials. Materials that are used. One is flash, another one is alkapine. Next. These are the properties of alkapine. Look at the fineness of alkapine. Look at the, it is 12,000 centimeters square per gram. That is specific surface. What is specific surface for OPC? Minimum 2,250 centimeters square per gram. Compare that one with this almost 8 times. So that much finer is that alkapine material is. Next. Other materials are sodium hydroxide, sodium silicate I am using. Next. Fine aggregate belonging to grading zone 2 I have used. With specific gravity 2.64, fineness modulus 2.79, coarse aggregate around specific gravity 2.73. I use the two fractions in the ratio of 3:2. It's 20 mm passing and 10 mm passing, two fractions. Next. This is the mix for one trial mix. I got so many trial mixes. Here I am presenting for one trial number 9. One mixture where you can see the flash content to be 342 kg per meter cube. Alkapine 38. Put together the binder is 380 kg. I am targeting M30 grade concrete. Fine aggregate 735 kg per meter cube. Coarse aggregate 1239. Sodium silicate solution 91.2 kg per meter cube. Sodium hydroxide solution 60.8. Extra water is 43.93 liters per meter cube. These are the ingredients for making 1 cubic meter of GPC. Okay. Next. And another big headache is you cannot use conventional tilting mixture for making this GPC. You have to use pan mixture. That's one thing. Next. These trials, you can see liquid to binder ratio is 0.4 is adopted. Water to geopolymer solids ratio is 0.3 adopted. Alkapine is varied from 0 to 25% for making these trials. Next. Now, for one mix, these are the results, wherein I am presenting the compressive strength versus AS for 3 different shapes of specimens. One 100 mm cube, another one is 150 mm cube, and another one is cylinder. What is your observation? See, general concept is that when you are expressing the strength per unit area, why should the specimen size influence your strength? That is a wrong concept. Your specimen size is having an impact on the strength of the material. Smaller the specimen size, more is the strength. Don't think that it is express resistance per unit area. But unfortunately, concrete is having this influence of specimen size. You can see that blue one, marker is the pointer is there. You can see the blue line, that is for 100 mm cube. Next, red one is 150 mm cube. Bottom one, green one is cylinder. So out of these 3 specimens, which is more reliable specimen for compressive strength of concrete determination? Have you seen? You know that any of these 3 can be used. One cube or one cylinder, which is more reliable. There's a different aspect. If you are interested, we can discuss later. Next slide, please. This one, split end, okay, title is wrong. Split tensile strength and flexural strength. You can see same trends as that of conventional concrete only. You can see that purple color split tensile strength, initial 7 days it is almost reaching 2 MPa, more than 2 MPa, whereas at 28 days it is 3.5 MPa or something like that for M30. Split tensile strength, obviously I expect around 10% of its compressive strength at 28 days, around. So that is meeting that one, requirement. Next, back 0.72 FCK is flexural strength, modulus of rupture, 0.7, 4.2 or something, 4.5 MPa, that is also giving you more than flexural strength is extremely good compared to conventional concrete. Next. Okay. All these investigations have been framed into 3 phases, phase 1, phase 2, phase 3. I don't know how much time I will get. In phase 1, this optimization of mix. Next. Phase 2, optimizing the water to geopolymer solid ratio effect on mechanical properties of geopolymer concrete. And in phase 3, I have discussed the durability studies like exposure to temperatures up to 800 degrees centigrade for different durations, 1 hour and 3 hours. Then how the impact is there, we have studied on M30 grade concrete. Next. Okay, this is compared to phase 1. Next. You can see here factors are first alkaline percentage. I have covered any pointer or anything like that. Okay. See, Salcofine I have covered in 6 dosages. 0%, 5%, 10, 15, 20, 25. And molarity of sodium hydroxide, that is chemistry. I have varied from 8, 10, 12, 3 levels only. And ratio of Na to SaO3 to NaOH, that is 3 ratios I have used. And I conducted tests on these parameters. What are the parameters? Compressive strength, flexural strength, split tensile strength as usual. In addition to that, static modulus of elasticity. How do I get static modulus of elasticity? There is modulus of elasticity. There is a separate apparatus you can find at the end of computers. Then UPV, using this value of UPV, ultrasonic pulse velocity, to calculate dynamic modulus of elasticity. Yes. There is an equation to calculate dynamic modulus of elasticity in terms of UPV. Next one. Experiment results based on these trials. You see how many trials? 17 trials were done based on this one. Next. Now you see on compressive strength the effect. Alcohol at different levels. These are the values. Compressive strength in MPa. You can see at third level 35.62,